trust me that's the case, then we can go ahead and try to analyze this conditional probability distribution that describes a channel and say, okay, for that channel, what's the best thing we can do in trying to decide what X was transmitted, and equivalently, if this is a one-to-one transformation, I know X, I know the message M that was transmitted. Okay, so we're going to assume that's okay for now. We'll come back to it, justify it later. We're going to study the detector, the decision device, if you will. And this implements a decision. You'll sometimes also hear the word decoder, decision, detector is another word often used and are all used interchangeably. And that's going to be a function of P of y given x, and of course x itself is tacitly there because it's part of this conditional distribution. Now, just before we do that, some algebra points, a couple of easy ones. Algebra, spell it correctly. Let me write these on a new page. There is a theorem in probability theory, basic probability theory, that if I have a random variable or random vector y, which has a probability distribution, P of y, and v is a dummy variable, v takes on all the possible vector values for y in the distribution, that this is equal to the sum from I equals 0 up to capital M minus 1, in other words, over the message set, P of y given x, which if we're using v as the dummy variable for y, we'll use I, since it's discrete, as a dummy variable for x, times the probability distribution of the input. And that should be a formula that's pretty familiar to you if you've taken a basic probability class. You can get the overall probability distribution for y if you have the conditional probability distribution and you just simply sum it over all the possible input values and multiply by the x distribution. Why do I care about this? Well, this is the channel. This is the vector channel here. So presumably I know that. And presumably also in my receiver, I know the probability of each of the messages. I don't know which message was transmitted. I'm going to try to decide that. Don't know for certain. But I could know the probability distribution of the input. Typically, they're all equally likely. So we just stick in 1 over capital M for P of x. But sometimes one message may be a little more likely, a little more probable than other messages. But if I know those two distributions, I can produce the distribution at the output. I may need this formula later in what we're going to proceed to do. Another formula, Ex, the energy. I equals 0 to capital M minus 1, summing over the message set, xi vector squared pxi. Basically, more clearly defining what energy means. Just take the probability of each of the messages, find the norm of the vector, and this is the average energy. Ey, the energy at the output of the channel, is going to be the sum, and here I'm going to write over V squared Py of V. So if I computed my output probability distribution, I can compute the energy at the output of the channel. Now, if it's a discrete channel which has a finite set of outputs, then this is a sum. If it's a continuous output, which can happen if the noise that is added, for instance, is continuous in distribution. So I take discrete and I add it to continuous, I get continuous in terms of the distribution. Then this becomes an integral and I have to add a dv over here. But it's still the same basic equation, sum of products, which is what an integral is doing, averaging the squared channel output vector. Okay, so these are three expressions. State them here, just headed into optimum detection theory that we may use to actually prove when we have an optimum detector. So let's get to that. Optimum DEC. The probability of error, which we call P sub E, is defined in transmission as the probability that the message decided by the DEC box is not equal to the actual message that was transmitted. Like in a good detector, or in fact in an optimum detector, which we're going to define optimum, will minimize this probability of message error, or of symbol error, if you will, in terms of transmission. The probability of being correct, of course, is the probability that m hat is equal to m, and that has to equal 1 minus the probability of error. So, again, minimizing probability of error will produce what we call an optimum decision, or optimum detector, or optimum receiver, if you like. Now, this type of receiver or decision device that minimizes the probability of error has a name, which you'll see often, called a map detector, where MAP stands for maximum a posteriori. We're going to see a reason for that particular name shortly. But the concept of this map detector starts by looking at the probability that we're correct. In other words, that the decision that's made by the detector, or the DEC box, is equal to a particular message that's transmitted when the receiver actually sees a specific output. That's a probability of being correct, is that the message is the actual one that was transmitted for any particular channel output vector that we happen to observe. Okay? Channel output is not really a distribution. It may be a random vector, but all the receiver sees is one sample from that. We're calling that V. It's got to base its decision on that, which we could actually write as the probability of M actually occurring, given that we've seen Y, MIV. Again, interpreting this quantity is saying I have a specific channel output. Okay, the probability of being correct given that output is just the probability that this message M sub I occurred. Okay, because that was the one that was transmitted. So what is that probability if the output is Y? That's a probability of being correct. Okay? Doesn't necessarily have to be 1. It could be some number less than 1. Okay? But that's the probability of being correct. Now, so this is, to write it in words, which I think helps, the probability that M hat equal MI is correct when Y equal V is observed. So that's the probability of being correct. So if I want to minimize the probability of error, I would maximize the probability of being correct. And so what I want to do is maximize P of M given Y, MIV, over the choices of M sub I. In other words, I'm going to choose that input message, okay, that maximizes this function for a given observed value at the channel output. Now, it may be for different channel outputs that different inputs maximize this function. But if I always choose the input that is most likely given that channel output, I will have maximized the probability of being correct, and in turn, I'll have minimized the probability of error. And because I've defined my optimum decision device as having minimized the probability of error, then this is the optimum detector. And so what it does is it maximizes this probability distribution is typically called the a posteriori probability distribution. It's basically a posteriori, which means essentially in Latin, looking backwards, okay, given an output, looking at the input. So that's where the name comes from. That is the optimum detector in communications. So let's look at an example, a simple example of this concept. Pretty easy to summarize, in one line, basically what an optimum detector is. What does it mean? How do we implement that? There are basically 4 classes here at Stanford that go into all the ramifications. Not even all the ramifications, just some of them. But let's take a simple example of that. Well, we have 2 possible inputs, x1 or x0, that could be transmitted through a channel. And we observe a single output y. It's kind of like binary transmission here, plus or minus 1 being sent. And let us suppose that there are only 4 outputs that we ever see from this channel. And they're going to be the numbers 3.1, 2.9, minus 2.7, and minus 3 for this channel. Those are the only 4 outputs we ever see. So this is a discrete output from this channel. And let us suppose that we know the probability distributions for each of these outputs. The probability that we get a plus 1, given that we see a 3.1, the output of the channel, is 0.9, which would mean that the probability of seeing a minus 1 given 3.1 is equal to 0.1, because 0.9 plus 0.1 add up to 1. Okay, given the same channel output, I can only have 2 possibilities. It's either a 1 or a minus 1. And I know the probabilities. I don't know what the message is at the receiver, but I know this a posteriori probability function. Now, how would I get that? Well, if you're familiar with basic probability, if you have P of y given x and you have P of x, you can actually compute this reverse probability distribution. It's a little exercise to go ahead and do that. We presume we've already done that here, so we have the a posteriori function. I could do that for each of these levels. Okay, somehow I have to characterize in terms of knowing what my channel is and knowing the 2 inputs to the channel. I go through the math, I work it out. Let's suppose, in this case I'm not going to write it all out, but probability of 1 given 2.9 is 0.85, which means the probability of minus 1 given a 2.9 output would be 0.15, because those 2 have to add to 1. And let's suppose down here the probability of minus 2.7, given that I've seen minus 2.7, of getting a plus 1 is 0.1, and the probability of getting a minus 1, given I've seen minus 2.7, is 0.9. And then finally, the last 2 here, 0.2 and 0.8. So I need those 8 numbers there basically to characterize this particular channel in terms of the a posteriori probabilities. If I have those a posteriori probabilities, I now know how to do an optimum detector. Okay? And the rule to minimum PE then is going to do, I can set up a little table here, tell us what to do. We've got 2 inputs, x, which are essentially 1 and 0 are the messages. That's this one or this one. We know that the actual symbol values are plus or minus 1 that correspond to those 2 messages. And we look at the possible outputs, V. So we're going to have 3.1, 2.9, minus 2.7, and minus 3. I'll get one of those 4 outputs at any point in time. If I receive 3.1, then the optimum detector rule says, go over here, okay, and say, I received 3.1. A 1 is more likely than a -1. So my decision here is going to be for message 1 and not for 0. So if 3.1 comes out, I decide message 1 was transmitted. Also, it turns out that if I see 2.9, the probability of 1 is still greater than the probability of -1. So I again decide message 1. Now clearly what happens down here is this, what happens is it reverses. The -1 is more likely, so in those 2 cases, I'm going to decide that 0 was transmitted. And for this particular channel, this simple decision rule for this vector channel will minimize the probability of making an error. What we've done is we've maximized the a posteriori probability. Okay, and you can actually work through the numbers to compute what the probability of error is going to be in this situation. It's basically the probability that 1 was transmitted but you decided 0, or equivalently that 0 was decided and 1 was transmitted. And you can add those 2 probabilities together and you'll get it. It's a simple exercise to do that here. But this is the basic concept, okay, of looking at the a posteriori probability and maximizing it. So you may ask, well, okay, great, how do I get this a posteriori? P of x given y from P of y given x, because that's what the vector channel is. That's what's given to me. Well, not too hard. There's a theorem called Bayes' theorem, basic probability, that says something like this. If I want P of x given y, it's simply P of y given x times P of x, all divided by P of y. And we already mentioned earlier that if I have P of y given x and P of x, I can compute P of y by summing over all the x values. So I can get these 3 probabilities, which allows me to compute the last probability, which is the one that I want to maximize in an optimum detector. So if I know the channel vector probability distribution, and I know P of x, the probability of the messages that are being transmitted, that's sufficient to be able to specify the optimum detector. I'll go through a little math exercise here. I'll compute P of x given y, and then I'll look for each output of the channel which x actually maximizes the probability of being correct for that observed output. And that equivalently minimizes probability of error. It's a pretty simple concept for the vector channel if I have P of y given x. Now, you will often see the term maximum likelihood detector, ML detector. In fact, more often than you'll see map detector used in communications. And this is basically the same thing for one particular input distribution. We're going to assume that all data symbols, all xi if you will, have the same probability. P x of I is equal to 1 over m, uniform. So if all the messages are equally likely, what happens over here in this particular rule that we're looking at, let's see here. I'm going to maximize this expression over x. Well, x only occurs in the numerator. I could virtually ignore the denominator because that's just a function of the received value y. Okay, but it would be the same for all values of x. So if I'm going to maximize this over x, that drops out of the maximization. So I could look at the numerator alone. Now if I look at the numerator alone, and P of x is not a function of x because it's uniform. It's 1 over m for each and every message. That drops out too. And so what I would do would be maximize P of y given x. That's kind of nice. If the input's uniform, I don't even have to worry about this Bayes' theorem and computing the a posteriori distribution. I can actually maximize what is called the likelihood function, P of y given x, over x, for any received value of y. And I will get what's called a maximum likelihood, or ML detector. And if the input distribution is uniform, that is in fact the optimum detector. If it's not uniform, it's an approximation to the optimum detector. It's not necessarily optimum any longer. But good transmission systems typically have the input adjusted, if you will, which means compressed. And if it is compressed, then it's basically going to have all messages being equally likely. Okay. An extreme case of having a bad design in communications, if you had one message that's far more likely than the other message being transmitted, why not just have a receiver that always decides the more likely message? Okay, and most of the time it's going to be correct. Okay, and then what that's telling you is, why do I even need to transmit? Okay, the receiver always decides the same thing, and that's ultimately implying that you could have transmitted the information with a lot less bits, a lot less information to represent it, if it's highly skewed